Good afternoon. Here we are for part 2 of lesson 8 of CENG 3325 structural analysis. So I'd like to move on and look at a brief example of the method of sections for trusses. So let's describe an example, and it can always be dangerous to do a problem on the fly, but we'll give it a chance and see how we do. Okay, let's work through an example problem on the method of sections. Method of sections, example. So as we mentioned previously in part 1 of this lecture, we saw that the method of sections was ideal for situations where you're interested in just maybe one member force or a series of member forces or a handful of member forces. It's not necessarily ideal if you are looking for every single force in every single member of a truss, or the forces in every single member of a truss. Is probably a better way to say that. So let's say we have a truss like this. And I'm going to try to draw a truss that would be very difficult to work with if we were doing this using the method of joints. So a nice, ugly truss. Or not ugly, but definitely beautiful, but maybe scary looking if you're considering using the method of joints to solve this. So something like this here. Oh, look at that. That's beautiful. Not ugly at all. Very beautiful, actually. Well, at least in terms of complexity. Alright, so let's consider this. Let's give some dimensions. Let's say this is, I don't know. Let's say this is 10 feet high. And let's say each of these, and this is not to scale, etc., etc. But let's give a distance for each of these as, I don't know, maybe 8 feet. 8 feet, 8 feet, 8 feet, so 8 feet, I'll just go down the line here. So 8 feet, 8 feet, 8 feet, 8 feet, and so on and so on and so on. And let's go ahead and say this is simply supported with a couple, and then with, of course, pin joints at each of the truss joints. So let's have a pin here and a roller here. Let's go ahead and put some forces on this, or a force on this. I'll keep it simple by just having one force on this. And maybe I can have a joint here, or a force here of 20 kips. Something relatively simple. Okay, so we have a 20 kip force along here, and then we have our two reaction forces. Now, we have a few ways we can do this. I think we might start by finding the reactions. So the reactions for this thing are going to be, we'll have, I'll just go ahead and call this joint. We can name these things whatever we want. Let's see. Instead of giving names to each and every joint, I might just name joints as I need them for simplicity. So let's call this joint A, and this joint B, and this joint C for now. Then I'll add more joint labels as I need when I do my method, when I actually take out my section of this truss. So my reaction forces here, I'll have AY, AX, which is going to be equal to 0 because there are no other horizontal forces on this, and then I'd have BY. Alright, so not going to be too difficult to get our reaction forces. Let's go ahead and get the reaction force at say, let me get the reaction force at A first. And I'm going to do this by summing moments about point B, counterclockwise positive. This is going to equal 0. And then I'm going to have 1, 2, 3, 4, 5, 6, 7. I'll double check that. 1, 2, or I can do it here. 1, 2, 3, 4, 5, 6. Sorry about that. 6. 6 bays to our 20 kip force here. So that's going to be 20 feet, or 20 kips. A force of 20 kips times a moment arm length of 8 feet times 6 here. 1, 2, 3, 4, 5, 6. And then minus AY times 8 feet times, there will be 8 bays there. 1, 2, 3, 4, 5, 6, actually 9. Sorry about that. I have trouble counting apparently. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. And all this equals 0. Now, I can just go ahead and cancel out the 8 feet, because that's going to be the same no matter what. And I suppose, the rest is fairly straightforward. AY is then going to equal 20 times 6 over 9. Not 69, 6 over 9. And that's going to be 2/3 of 20, so 20 times 6 over 9. 20 times 6 over 9, and we have that times 2, that would be 13.33 kips. Then I can just do a sum of forces in the vertical direction. Sum of forces in the vertical direction. This is going to be equal to 0, of course, and I will have, let's say AY plus BY minus 20 is equal to 0. And then BY is equal to 20 minus AY, which is equal to 20 minus 13.333. And then that's going to equal 20 minus this. And we have 6.666 kips. So nice lucky reaction there. Now, so let's say this was given, and let's say I'm asked to find the force in a certain member. And we could pick any member we want, but let's say I want to find the force in this member here, the circled member. Find the force in the circled member. Now, let's talk about how difficult this would be if I was using the method of joints. So I have my reactions, so I've made some progress, but if I wanted to solve this using the method of joints, well, the logical place to start would be at joint A. I would solve equilibrium about joint A, get this force and this force. Then, well, I would still have some problems. I couldn't use this joint here just yet, because I would have 3 unknowns, so I'd have to go to get this joint, get this one and this one. Then I couldn't go here quite yet because I'd have 3 unknowns, so I'd have to basically go here. I'd start at joint A, then I'd have to go here, to here, to here, to here, and then maybe I could solve for equilibrium about that joint. So I'm going to have to do 1, 2, 3, 4, 5 different joints and sets of equilibrium equations before I can finally get my desired joint. And that's if I'm working from the ideal end. The ideal way to solve this using the method of joints would be to start from this end here, the left end. A much more daunting and convoluted way would be to start from joint B and work my way across, and that would be an even greater number of joints and equations of equilibrium. So, but we can jump much more quickly to our solution here using the method of sections. So what I'm going to do is I want to look at what section I might take. So looking at my guidelines from last time, I'm looking for a section that I want to cut across members, not through joints. I want to include all the desired member forces and include no more than 3 cut members. So looking at this, I think I'm going to make a cut. Let me show you where. I think I'm going to make a cut. Let's do it in yellow here, or maybe light green. I think a good cut would be right here. Right like this. I'm just going to cut out the left end of the truss, and that's going to cover 3 forces, or that's going to cut through 3 members, and in turn that's going to reveal 3 member forces. So I'm going to have these forces here, here, and here, and I'll have those 3 member forces will be revealed, and then also have my reactions. Now, interestingly enough, what is going to be cut out is our reaction force, or our applied point force here. And that's actually not going to appear anywhere on my free body diagram for my section. So this is kind of interesting. I do like using this section because it illustrates that when we cut something out, we only have to look at the forces that are in that section. So the reaction force, so you might wonder, well, how does that force have an effect? Well, it's already baked into our AY. So let's look at a free body diagram of just this section here. And what I'm going to do is I'm going to replace this entire section with sort of just a block. to show that I'm treating it as a single rigid body, and then I'm going to replace any of the cut members with just a simple line force. And I'll also put any kind of force triangle on there to illustrate any slopes, etc. And I think, as I said, we're going to need some more forces, or joint names. So I'm going to call this joint D, this joint E, and I'll call this joint F here. So I'm going to have this section here, and I'm going to probably bounce back and forth a bit here. And it's kind of I'm kind of treating it like a block. Maybe I'll draw it a little bigger, actually. And so here is my cutout section. It's like this. And to really drive home the point that I'm ignoring any internal, any member forces inside the block, I'm not even going to bother drawing the internal members. To drive home the point that I'm treating this as a single isolated rigid body. Dimensions on this, again, nice to scale drawing. 8 feet and 8 feet like before. Then I have 10 feet from here to here. From here to here. Then, showing the forces on here, I'm going to call this, let's see, the force from this cut member, I'm going to call that FCD. And then down here, I'm going to have FEF. Then at an angle, coming up here, I'm going to have force FCE. And I do want to get the force triangle for this. This is going to be at a, let's see. Well, in height, this is going to be 8 and 10, which is the same as 4 and 5. So this isn't a 3, 4, 5 triangle. Oh, got that a little backwards. That's a 5 and a 4, not a 4 and a 5. So 5 and 4, so I'm just going to go ahead and get the Pythagorean of that, or take the square root of the sum of the squares. Ask my old buddy Pythagoras, and he tells me that this thing has a length along the hypotenuse of 6.403 feet, or actually times 2 for the rate, but I'm just looking at the ratios here. Then, let's see, so other points we have point C up here. I got that right? Yes, point C up here is where that 20 kip force is applied. Let's see, this is point E here, and this is point D. And the force that I'm looking for is member EF. And then the other force that we have on here is our AY, which is equal to 13.333 kips. Now, actually, it turns out I didn't even need to get that force triangle because of this particular problem, the way I phrased it, I'm not looking for all of the forces that my cut is coming across. I'm actually only looking for FEF. That's all I'm looking for. So if that's all I'm asked for, if that's for whatever reason all I'm interested in, well, you know, I'm incredibly lazy, so if I can find a way to save a bit of time, I'm going to do that. So if I don't need this force here and this force here, I have any number of ways I could solve for these. So if I did want this force, I could say if I wanted this force here, FCE, the easiest way would probably be to sum forces in the vertical direction. Because this unknown force and this unknown force are horizontal, this would be the only one with a vertical component. I could solve for that very quickly. Or if I was interested in this force, I'd probably want to sum moments about point E, because neither this force nor this force will generate a moment about E. Again, that will produce a result fairly quickly. Oh, and I'd probably also want to mention the dimension from here to here is also going to be 8 feet, because that's going to be important. But if all I'm interested is in the member force in member FEF, I think I'm going to just do I'm going to jump to this very quickly and very simply by doing a sum of moments about point C. Why did I choose that? Well, looking here, FCD and FCE are again, these come from the two cut member forces. Every time I cut across a member, I'm going to generate an unknown force. And just as I did in the method of joints, I always just assume it's, I make the lazy assumption that everything's in tension, and then if I get a negative number, I know that it's going to be in compression. Simple enough. But how did I notice some moments there? Again, I know that FCE and FCD, because both of these members go through point C, neither of them will generate a moment about there because their line of action, the line of action of their axial force goes through point C. So I can just sum moments about C, and those two forces, they have no moment arms, so they just go away, poof, they're no longer here. So I need the only two forces that will generate any moment there, the only two forces on my free body diagram here that'll generate any moment there are FEF and the reaction force AY. And again, this is kind of interesting. Even though our applied force, the 20 kip force, is applied at point C, it doesn't matter. We still don't need to include it. And the reason for that is because we isolated just the section on the left. And again, if something is, as we learned last time, as we reviewed last time, if an object is going to be in equilibrium, every piece of that object must be in equilibrium, and every piece of that object must be in equilibrium about any point in space. So I should be able to cut out one section of that truss, take equilibrium about any convenient or given point, and that I should be able to reach a solution very quickly. Anyway, let's go ahead and work through that. So I'll have, let's see, 13.33 kips. And this is going to be a negative moment here, times a moment arm length of 8 feet, times 3 bays. Not 3 feet, but 3 bays. So I have 8, 8, and 8 to joint C from the reaction arm, or the moment arm, or sorry, that's the length of the moment arm, to the reaction force AY here. And then these are of course going to generate a negative moment because they're rotating clockwise about point C, that force is. Then plus FEF, if I can manage to write the letter E, and this is going to be a positive moment about joint C or point C because that is a negative counterclockwise rotation, times a moment arm length of 10 feet equals 0. So if I multiply 13.333 times 8 times 3, but it keeps wanting to jump forward here on me, I can get the FEF. If I move that to the other side, that is then 319.99 kips over 10 feet. Oop. Which leads to that, not 2 E's, derp, FEF, which leads to this is equal to about 32 kips in tension. So FEF, simple enough, that FEF is going to be equal to 32 kips in tension. And this shouldn't be any surprise. We saw that it, as we've seen in previous videos, previous lectures, that for a truss that is simply supported in positive bending, generally, there may be some weird exceptions, but at least for a single span, simply supported truss, aside from any unusual exceptions, your bottom chord will be in tension, your positive chord will be in compression, so no surprises there. Alright, that'll do it for this video. I just wanted to do a very brief video on solving for truss member forces using the method of sections. That'll do it. Let's see. Thank you for watching, and as always, thank you.